Hi, this is going to be the test review on states of matter. This unit is a little bit of a fun chapter relative to what it says about nature. You're going to be surprised about some of the concepts. You're going to be surprised that you were living under a misconception about certain physical phenomena in nature. It's going to explain things that will surprise you. So the lecture is over 2 hours and 30 minutes. It's very long. I would suggest, and I'm going to suggest, starting the chapter with this review. And as soon as you hear this review, take heed from this. And that is that you should start looking at the lecture immediately. As soon as you find out this, you should look at the lecture, and you should look at it in pieces, 15-20 minutes. Rip it from YouTube and put it on an iPod, something. But you should start early. You can't possibly listen to a 2 hour and 30-minute lecture in one sitting. You'll go out of your mind. It's not Star Wars. It's not that interesting. So you want to do it in pieces. Set up a schedule where you're going to do it in pieces, small pieces, on a regular basis until you're finished with it. And then use that as a guide for studying the chapter. And you can use that as an outline. There's a lot in there. There's things that are not in the text but are on the test. And if I see an outline with information from that lecture, I'll give you a lot of extra credit. So that's going to be a lot of extra credit, and that's going to be your incentive. If you want some extra credit, this is how you get it. Take notes on that lecture. Instead of reading the book, save that time that it would take to read the book. Don't read the book, and listen to the lecture. Okay? Listen to the lecture. And there are also problems from the back of the chapter that are solved in another lecture from this unit. So this is going to be a more complete chapter relative to resources that are available to you. So let's begin right away. You're going to need to know there's matching. There's 3 sets of matching, first 15 problems. So this is going to be an easy start to the test. Unit cell. What's a unit cell? That's with solids. Crystal, allotropes, amorphous solids. So that's solids. Here's one: melting point, boiling point, sublimation, evaporation, vaporization, normal boiling point. Those are things that you learned in middle school, but have significant meaning relative to this new unit. Here's another set: kinetic theory, atmospheric pressure, vapor pressure, a barometer, and kinetic energy. We don't really talk about barometers very much in our daily lives, but in the United States, the pressure is given every time there is a weather forecast. The barometer is given. The barometer is used, and the pressure is given by the weather forecaster. So a barometer is used to measure pressure and atmospheric pressure relative to this chapter. You've got to know the kinetic theory and what the kinetic theory means relative to the movement of molecules. When the kinetic energy of a molecule increases, its speed increases. A molecule will move in a straight line, not a circular pathway, but a straight pathway, until it hits another molecule and then it bounces. So the number of collisions, given a set of molecules, let's say a gas, where they're far apart, if I increase the kinetic energy of the particle, I'm going to increase its speed. If I increase its speed, and velocity, of course, because we're talking about direction, which way is it moving, it will stay in that straight line forever, unless it collides with another particle. And it will collide with another particle. And I'm going to tell you why. You understand the concept of heat. Well, collisions create friction. And that friction is given off as heat. And what we do is this: we measure the relative temperature of a system based on the kinetic energy, the friction that's given off as a result of the kinetic energy of the molecule. That's how we measure temperature. We say, okay, how do we measure the relative kinetic energy of a gas? We measure its temperature. And the temperature is the heat that's given off with the collisions. When a molecule is moving, you can't measure its heat. You can measure its kinetic energy, if you wanted to, by the 1/2 the mass times the velocity squared. However, what we do is we say, let's let the molecule collide with other molecules in a gas or whatever particles. And the collisions that occur are going to create a temperature, a heat environment because of the friction. The friction is going to give off heat. So what we do is we measure the amount of heat that's given off as a result of these frictions, and that's a temperature. And we call that the temperature of the system. If you increase the kinetic energy, if I heat the particles, and the molecules will move faster. If they move faster, they're going to have more collisions. They have more collisions, more friction, more heat. And the temperature is going to rise. So when you increase the kinetic energy of a system, you're increasing its kinetic energy, or the individual particle's kinetic energy, and one thing leads to another, and you're going to create more heat. And that's really what temperature, heat, kinetic energy, that's the relationship among those three ideas. We have to know the idea of an elastic versus an inelastic collision. Remember, an elastic collision is when two things collide and they bounce away from each other and they don't lose any energy. Well, if they don't lose any energy, there's no friction. If there's no friction, there's no heat exchange. So if you have a gas that has collisions that are perfectly elastic, you're not going to have any heat at all. All the energy is going to be given off as nothing. I mean, you're not going to have any heat given off. You're just going to have these collisions, and if everything is elastic, nothing's lost in the environment. If I bounce a ball, if I drop a ball, a super ball, it's going to bounce high as opposed to like a tennis ball. But it's not going to reach my hand because some of the energy was lost to the floor. Can I measure that energy loss? Of course. Would it be difficult? Absolutely. But if you take your hand and you pound on a desk with your hand, like you're drumming a song, like Wipeout, God, 1960s, early 1960s, and I think we'll have done that in class by the time you listen to this. You're gonna heat the desk up. You're gonna heat your hand up. I'm gonna have you feel your hand after you pound on the desk for a while, and you'll feel the heat, because those collisions are not elastic; they're inelastic. What does that mean? Well, some of the energy was lost, and it's usually in the form of heat. Could be usually in the form of heat, because you have that collision, the friction, you're transferring the energies, etc. So if I heat a gas, and I combine it with oxygen, and it gives off this amazing amount of heat, that kinetic energy of those gas molecules, of the air molecules, because the flame's coming out, okay, and you're heating the air molecules, and you're heating the gas molecules, and the carbon dioxide in water is heating, and you get that blue flame, and the kinetic energy of all the gas that's underneath the pot is high. You're increasing it. You're pumping enormous amounts of energy, and that's kind of creating, that's increasing the kinetic energy of the metal, the copper in the bottom of the pot, or the stainless steel, or whatever the pot is made of, and then that kinetic energy is going to be transferred to the water that you're heating. So we're talking about the conduction of heat from the explosion of the methane or propane or butane and oxygen to form the carbon dioxide in water, which are going to have enormous quantities of heat produced as well. Why? Because the energy level of the methane and oxygen before reaction is very high, the energy level of the carbon dioxide in water is extremely, and I say extremely low. So the energy difference is the energy given off. So that's where I'm getting that heat energy from. My initial heat energy is coming from that. And then you're taking that heat energy and you're heating all of these molecules of air and gas and product, and then the metal, and then the water, etc. And that's conduction. And we'll look at what's radiation and what's convection. Right. You're going to look at like who made up the kinetic theory. We want to look at some of the scientists that came up with these concepts like kinetic and potential energy. What is the kinetic theory of gases? Look at these four things. You're going to need to know these: thermometer, barometer, vacuum, and manometer. What's a manometer? manometer. And we're going to look at a bunch of manometers. I'm going to give you some problems relative to manometers. What is a kilopascal? What is a pascal? Remember, this is key. If I have a pressure of 1 Newton, what's a Newton? I'll explain in a minute. 1 Newton per square meter. 1 Newton per square meter. That is a pascal. So think about this. What is a Newton, first of all? All right, well, let's look at what a Newton is. All right. A Newton is a force. Pressure is a force per unit area. The unit area we use in atmospheric pressure is called a pascal, or related to pascals. A pascal, the unit area for a pascal is square meter. The unit area for pascal is a square meter. So what's a Newton? Well, according to Newton's second law, and we'll go over this, second law of motion, force is equal to the product of a mass times its acceleration. So what does that mean? You have a mass, right? You have a mass, and you are accelerating. You're sitting in your chair. Well, you are accelerating, but something's stopping you from continuing to accelerate down. So in other words, if you jump out of a plane, you're going to accelerate down. Well, you're accelerating right now, but something's pushing against you to stop you from accelerating, but you want to accelerate. You are accelerating, but something's stopping you from accelerating, and it's the chair. And if you think about it right now, in the chair you're sitting, you feel yourself, feel the chair. Do you feel the chair? Well, that chair, according to Newton's third law, is pushing back with an equal force that you're applying to the chair. Well, the force that you're applying to the chair is equal to the product of your mass times the acceleration due to gravity, which is 9.8 meters per second squared, which means that if I drop a pencil, let's say 10 meters per second squared, just easier. If I drop a pencil, according to Newton's laws, that pencil is going to accelerate at 10 meters per second squared. It's going to accelerate at 10 meters per second every second, right? So it's going to accelerate 10 meters per second every second. So at the end of the first second, it's going to be moving 10 meters per second. At the end of the second second, it's going to be moving 20 meters per second. At the end of the third second, it's going to be moving 30 meters per second. That's what it means, 10 meters per second squared. Every second, it's going to increase its velocity down, speed down. Velocity is speed and direction. It's going to increase its speed, its velocity, 10 meters per second. So at the end of 10 seconds, it's going to be moving 100 meters per second squared. So if you take your mass and multiply it by 10, that's your force. And the unit labels for mass are kilograms. The unit labels for acceleration are meters per second squared, and the unit labels for force would be, look at it carefully, would be kilogram meters per second squared. But we have a way of saying kilogram meters per second squared. Kilograms times meters per second squared is kilogram meters per second squared. And we call a kilogram meter per second squared a Newton. That's what we call a Newton. I'm going to take a break, and you'll never know I was gone. So let's consider the fact that I have a 1 cubic meter box. So 1 square meter up top, so a meter wide, a meter long, a meter high, 1 cubic meter. So on the floor, it's leaving a pattern of 1 square meter. I fill that with water. I can put in there 1,000 kilograms. So 1,000 kilograms times 10 is going to be 10,000 newtons. So it's 10,000 newtons per 10,000 newtons per square meter. Okay, that's heavy. Can you imagine being under that? That is a metric ton, 2,200 pounds. Very, very, very heavy. A lot of weight. Okay. Now, if you put 10 of those on top of each other, that's 100,000 newtons per square meter. Now, a newton per square meter is a pascal. A newton per meter is a pascal. So that's 100,000 pascals per square meter. And that is equivalent to 1 complete and absolute air pressure, 1 atmosphere of air pressure. So that's the pressure. That's an equivalent measure of the pressure of a column of air, which is 1 square meter around, okay, and very high, but it will, if you look at the floor where you're sitting, look at 1 square meter on the floor, and that column of air that's sitting on there, that's resting on there, goes way up hundreds of meters, and that is going to be equivalent to 10 giant boxes of water, where each box is 1 cubic meter. Same idea. There's somebody drilling next door, so it's gonna be a little weird trying to listen. So that's 1 atmosphere. So that's 100,000 pascals, or 100 kilopascals. And 100 kilopascals is 1 atmosphere. Oh, 101.3, but who's counting? It's 100,000 or 100 kilopascals. 100,000 pascals or 100 kilopascals. So that's going to be 1 standard atmosphere of pressure in kilopascals. 100 or 101.3. Okay. Now, you need to know about if I go down through the ocean. So I go down through the ocean 10.3 meters, say 10 meters underneath the surface of the ocean. Right. How many atmospheres is that equivalent to? So every 10 meters I go down in the ocean, every 30 feet, how many atmospheres is that equivalent to? What can flow? Think about it. Can a solid flow? Think of concrete. Can buildings flow? No, of course not. If they're built on water, they can flow, but can the concrete itself flow once it's hardened? Absolutely not. Once it's a solid. The concept of concrete also is very important. We'll talk about how concrete forms a solid and what keeps it that way. You know what keeps concrete solid? Water. Yeah, the covalent bonding of water to the internal structure of the concrete and the matrix, the cement, the sand, the particulates that are in the concrete, such as pebbles and stones, etc. What happens to the temperature of a liquid that when you evaporate? Okay, we have a liquid. All right, water's evaporating. Well, what's it taking with it when it evaporates? Let me ask you a question. Is evaporation a heating process or a cooling process? All right, that's number one. Condensation, is that a heating process or a cooling process? When you're in the shower, the water is condensing. You see that steam. Is that a cooling process or is it a heating process? Condensation. Okay. Let's see, what else? What's the relationship between kinetic energy and temperature? What's the relationship between kinetic energy and phase? Phase meaning solid, liquid, or gas. Again, what's the relationship between evaporation and the cooling or the heating of a liquid? What's boiling? Define the word boiling. What's sublimation? What's deposition? Let's see. Why does hot water, when you let's say you go out and it's really cold, and I'm talking -20 outside, and you throw a pan of boiling water up in the air and it turns to snow. Why does that happen? Does it happen with cold water as quickly? Interesting. Look at the internet. Try to find some YouTubes on that. What is the relationship between, here, I'll read you a problem. If a liquid is sealed in a container and kept at constant temperature, how does its vapor pressure change over time? All right, here's another one. What is the difference between the vapor pressure of water compared to the vapor pressure of acetone? What is the relationship between the vapor pressure difference between acetone and water? Okay, here's another one. What is the relationship between vapor pressure of water and vapor pressure of ethyl alcohol? All right, here's another one. Let's see. You add energy to a boiling liquid. What happens to the temperature of the liquid? You're not changing the pressure, though. What's the relationship between pressure and boiling point of a liquid? Very interesting. Curious. Where would you think that water might boil at 105 degrees Celsius? Where could that happen? With just a placement, geographical placement, with no special equipment. Well, you're going to need special equipment, hint, hint, but it's just a geographical change. Okay, here's one for you. When the external pressure is 505 kilopascals, what is the vapor pressure of water at its boiling point? Okay, here's another one. What is the relationship between chloroform and water relative to vapor pressure and boiling point? Okay, that's it. That's all she wrote. It's going to be a very interesting unit, really. I'll give you another one. I'll leave you with this. I'll leave you with 4 things. Define hot, define cold, define burn, and define frostbite. There you go. Have a great test. It's not going to be for a while, but I'm going to publish this right away. And I would suggest listening to this right away. It's only going to be, I don't know, not very long actually. 25 minutes. Listen to it a few times. It'll get you centered for the next unit. I'm getting a little tired of moles and stoichiometry, to be honest with you, and so are you, I'll bet. There's going to be a little bit of a break from that. We'll get back to it, but not right away. So we're going to take a unit off. When we do gases, we'll get back to moles and etc. But right now, we're taking a moment off. We're doing a chapter really without calculations. Well, not a lot of them anyway. So anyway, have a great time studying, and let's hope for the best. Take care. Bye.